All right, we're going to do a quick video here on counting principles. This is not a direct lesson in statistics, but it gets used in other lessons, so we need to know this in case you didn't know this already. This might be familiar to some, might not be to others. We'll try to make this real quick. All right, so here's an example. Papa Murphy's has 3 different types of crust, 2 sauces, and 10 toppings. We don't know how many different one-topping pizzas can be ordered. So how many different combinations of these can you do? Well, if you, like me, thought, well, I can start making a tree diagram. One crust, another crust, another crust. From each crust, we could have 2 sauces. From each sauce, we could have 10 different, I can't even fit that many on there. But ultimately, to find how many total, I could just take, there's 3 crusts, 2 sauces, and 10 toppings, and that gets me 60 total combos of pizza. And that's our basic fundamental idea of counting. All right, so the fundamental counting principle basically states that when there are m number of ways to do one thing and n number of ways to do another, you can multiply those two together to get the how many ways there are of doing both. Okay, kind of like with multiplying probabilities together with an and, it's the same idea with just finding totals. But some situations aren't quite as simple as this one. So let's get into a couple, and then I'll give you a rundown of what we're talking about here. So how many ways can I order 3 books? Just 3 books. I could order book A, B, and C. I could order book A, C, B, or I could order book, we can order 3 different books. Basically, the way we look at it is there are 3 options for your first book, right? You can say book A, B, and C. So you have 3 options for your second book, or for your first book. Second book, well, you can't order the same book, okay? So we're going to say there's only 2 options, and now you're down to 1 option for your third one. So if we're using that fundamental counting principle, it's 3 times 2 times 1, which is 6. All right, you could write all the different combinations, and there's 6. If this looks familiar to you, that's great. If not, when you multiply a number by every individual whole number underneath it, not including 0, because that's not a whole number, that is called factorial. So on your calculator, maybe you see an exclamation point somewhere. That is factorial. That means 3 times 2 times 1. Likewise, if I were to do, this is totally side note, like 6 factorial, that means 6 times 5 times 4 times 3 times 2 times 1. So on your calculator, which I can show you here, nope, I can show you here, there is a way to do factorial. There's, if you can find the exclamation point. Oops, sorry about that. So if I take 3 and I want to do factorial, 3 is a small number, but I'm going to go to math and I'm going to go over to probability. We're going to use that for a few things here. Number 4, it's an exclamation point, and I've got 3 factorial is 6. 3 times 2 times 1 is 6. All right, back to this. That idea works with this one because a couple notes. There are the order does matter. That's a big thing we're going to talk about. In this case, there's also no replacement. So it changes a little bit if you can repeat things or replace things. So no repeats in this case. All right, let's say I have 5 books. How many ways can I order 3 of them? And again, no repeats. Order does matter. So now you have 5 options for the first book. You have 4 options for the second book. You only have 3 options for the third book. And we only want 3 books. So that's using the fundamental counting principle here, we can get 5 times 4 times 3, which gets me 60. There's 60 different book combinations of 3 books. Now, how can we use that with factorial? Because 5 times 4 times 3 isn't factorial. So if I wanted to factorial that exclamation point, that means 5 times 4 times 3 times 2 times 1. So how do I get rid of that 2 times 1? Well, I divide it by 2 times 1. So basically what I did there was I did my 5 minus the 3 combinations that I did, factorial. And that'll get us into a formula that we're going to use in just a little bit. So that's a full factorial situation there. All right. Last example before we get into what is what. I have 5 books. How many ways can I choose 3 to read? So I'm just choosing 3. Does the order matter? No. So in this case, the order does not matter. Now, if I go back to my options, for books A, B, and C, let's just say you have, for choosing 3 things, you could do A, B, C, separate from this 5 books thing. A, B, C, you could do A, C, B, you could do B, C, A, B, A, C, C, A, B, and C, B, A. So really there's like 6, whereas if order doesn't matter, A, B, C. Like order doesn't matter. It can just be those 3 books. So literally there is 1/6 of the amount when the order doesn't matter. And that has to do with the fact that I had 3. Remember 3 factorial? So it's 1 over however many I choose factorial. So if I am doing 5 books, which we said was going to be 5 times 4 times 3. If I want to do this again, and do my 5 minus 3 factorial, that I would have to multiply by 1 over 6, which is that 3 factorial. Now, that's a lot of writing, and you can figure this out other ways, but there's actually a really easy way we're going to use this today, and something that you can use going forward. So one of these things that we just talked about is a permutation. A permutation is an arrangement of objects in a specific order. So order matters. Order is important. Big stars there. So like ABC is different than BCA or other arrangements of that same thing. Now, I'm going to give you a couple of ways that you might see this. So P, N, and R is a permutation. More commonly, we're going to use P with the N and the R like this. You'll see that on the calculator as well. But ultimately what that means is N factorial divided by N minus R factorial. So it's like that formula we just kind of came up with, where we'll say N equals the number of things or objects or options, and R is the number we're choosing. How many we're choosing. All right. So you kind of say that's N choose R, but we're going to use that for the next one. So this is a calculator function. So let's just say back to our other one, we had five books, we wanted to choose 3. I would say this. And on my calculator, which I'm going to show you now, whoops, right here, we can go back to our probability, so our math, go over to probability, go down, you can see there is NPR and NCR. We're going to use the P for this one, and now depending on the calculator, you might have to type in a number first. For this one, I can put that in, I can put 5 here, and I can put 3 here. Okay? I get 60, which is the same answer we got before. Beautiful. Let's go to the next thing. The other thing is when order doesn't matter. So there's a significantly less number of options if order doesn't matter. So if it is a selection of objects without replacement, without regard to order. So order does not matter. Big note there, order does not matter. You just want to know how many combinations. It doesn't matter what the order there. So ABC is the same as BCA and all those other ones. So there's only 1 instead of 6 different options there. And this is often read or noted as, you might see it like this with the N and the R again. So it's a combination. More commonly, we're going to use this one. Or we'll see it like this. N choose R. Okay? N choose R is kind of how you might read that. N choose R. But the formula is N factorial over N minus R factorial. But that is multiplied by R factorial, which we kind of came up with in our last example as well. I want to show you that formula, but you're going to mostly use your calculator. So in the calculator, once again, This is like that last example here, where I guess we didn't actually answer it, but it ends up being 20. So we have, I think it was 20 options for that one, where the order does not matter. Let's say we have 5 books and we're choosing 3, but the order does not matter. So let's go back to our calculator and use the combination. So probability, using the combination, I'm going to put in 5, I'm going to choose, go over, choose 3, and I get 10. Yeah, it was 1/6 that I said it was going to be 6 times less. So 10, not 20. So that's how we can use our calculator. Now, I'm just going to give you some different examples here of permutations or combinations. You really just need to know the difference, and then you can use your calculator for these. So there are 5 finalists in a beauty pageant. In how many ways can the winning and runner-up, so 2 people, be selected? So in this one, does order matter? Yes, order matters. So I would take this and I would go P, this is my one with order matters. There's 5 options. We're choosing 2. And I can use my calculator. So I'm going to do a couple on the calculator so you can see it, and then we'll do a couple where you have to do it yourself. So this is a permutation because the order matters. Math, probability, down to permutation. If you have a calculator where it doesn't let you put them in like this, you might just have to, you would just have to type in a number first, and then hit that button, and then type in the second number after it. So the end would come first. In this case, it's 5, choose 2. Permutation, enter, I would get 20 different possible combinations. All right? 20 different ways that would work. All right, let's say we have a coach determining a batting order for a 9-member team. So you have 9 people out on the field at a time. If you play baseball or softball, you understand that there's a batting order. So order does matter. When you see that order, bingo. So this is a permutation. Order matters. You have 9. You're choosing 9. You're using all 9. So calculator. 9, choose 9. Permutation. I'm going to actually hit second enter. I'm going to put these. I'm going to change these numbers. That's a 9. That's a 9. And I'm going to hit enter. Wow. There is lots of ways that you could order them. 362,880 ways. It's a lot. That's what a baseball manager has to think about every day. Let's take a look at a couple other examples. I'm going to jump straight to here. Let's say there's 8 people in a room. In how many ways can you select 5 of them? Does the order matter? No, you just want 5 people. So how many different groups of 5 are there? So order does not matter for this one. So it is a combination. So using my combination, this would be a combination of 8, choose 5, and I'm going to go to the calculator. Way faster if I can use this calculator to figure out the combination here. So 8, choosing 5, and I got 56 different ways. Now, generally, your numbers are going to be lower with combinations because the order doesn't matter. A drug is tested on 20 people, and how many ways can it work on 5 randomly selected people? Does the order matter? No. We just want 5 people from the 20, so this is a combination of 20, choose 5. So last one on the calculator, then you're going to have to do the rest on your own in the calculator. We're going to change this to 20, choose 5, choose 0, hit enter. 15,504. I'd hate to make a tree diagram for that many random people. So, last example, you can just, hold on. Yeah, last one here. From a group of 7 people, how many groups of 2 people can be created? Combination or permutation? Order doesn't matter. It's just groups of 2. So it is a combination. 7 people choosing 2. Go to your calculator and find that probability. You should get 21. There's 21 different groups or combos. All right, I'm not going to go through all these, but I want just you to think about whether these would be combinations or permutations. When it says how many different ways can a family have 5 children? A family of 5 children have 4 boys, 4 girls, 2 boys, 3 girls. There are some similarities between these, and I want you to think about, is this combination or permutation? Does order matter when you're dealing with different ways to have a family of 5? All right, and that is our day on counting principles. We'll see you next time.